Pure variational calculus is intimidating. For engineers approaching structural simulation, the complexity of the underlying math often creates a barrier to entry. Hamilton's principle defines the path of a dynamic system. We are going to separate that identity as a physics concept from its utility as a practical engineering tool. Our objective is the translation of continuous, complex physical reality into a discrete, solvable, finite element analysis system. A mathematician seeks a rigorous proof, but a structural engineer needs a functional, safe method to predict how a bridge responds to a load. If you already have a working intuition of Hamilton's principle, this introductory primer is likely unnecessary for you. We are speaking to engineers moving into structural simulation who need operational tools rather than theoretical derivation. Effective finite element modeling doesn't require mastery of infinite mathematics. It requires a specific mathematical filter to extract the data needed for the simulation. This series follows a specific instructional philosophy, the operational toolkit. We make a deliberate choice to simplify the mathematics. We select only the variables required to perform engineering work, setting the rest aside. While omitting the broader foundation, these extracted tools lock into your software, building standard FEA models without errors. Traditional academic teaching often requires exhaustive theoretical proofs before ever reaching a practical application. The goal here is structural formulation, setting up the problem so the computer can solve it. To use this method, you must focus on the application of the tool rather than the derivation of every underlying proof. These simplified mechanics serve as the bridge from basic solid mechanics into computer simulation. To build this bridge, we extract two specific functional tools from the field of variational methods. The first is the concept of energy. The second is the concept of variation. Combining these two tools allows us to bypass traditional force balancing equations. Instead of tracking every vector, we look for the system's lowest energy state. We then integrate this minimum energy principle into the core logic of the FEA software. This creates a scalable system. The software uses this logic to solve hundreds of interconnected nodes simultaneously, removing the need for manual calculus at every connection. The software handles the exhaustive computation. Your role is to define the initial energy state and the constraints of the system correctly. If the initial energy state is defined incorrectly, the automated system will process the data and fail without warning. Simplified math requires higher precision in how the problem is set up. Once established, this setup works for nearly all subsequent structural analyses. This process converts a complex theoretical physics concept into a programmable engineering algorithm. This toolkit is only effective if it is grounded in physical intuition. You must have a working knowledge of basic beam theory before applying these models. We are building a conceptual bridge between a physical beam and the discrete nodes of a simulated model. There is a difference between understanding how a beam bends and knowing the mathematical mechanism used to calculate that bend. Your intuition as an engineer acts as the safety check. You must recognize if the simplified model results match physical reality. These variational tools map directly onto the nodes and elements of your beam schematic. Removing the complex math is only safe when you have a firm grasp of fundamental physical mechanics. Relying on an operational toolkit has specific limitations. We have to define the boundary where these simplified methods are no longer applicable. In this efficiency zone, the simplified math provides reliable accuracy for standard, linear structural problems. But as the complexity of the problem increases, we cross a threshold where the simplified approach is no longer accurate. Advanced problems, such as nonlinear materials or theoretical research, require a return to more complex variational calculus. For the requirements of this course and the following analyses, we will remain safely within the efficiency zone. Knowing when a mathematical tool will fail is as important as knowing how to use it. Now that we have defined these limits, we can begin building our first model. By applying our toolkit, we take a continuous wireframe and divide it into discrete elements. This step addresses the transition from a continuous physical beam to a solvable, discrete framework, the core requirement of finite element modeling. You now have the principles required to start active problem solving. For an engineer, a functional working simulation provides more utility than a rigorous but unusable mathematical proof. We are moving from preparation to execution. In the next module, we will convert these energy principles into matrices. Matrix derivation is our goal, as matrices are the primary language used by modern FEA software. The upcoming lessons will focus entirely on applied analysis. As we increase the structural complexity, remember the operational boundaries we established. The groundwork is set. Applied matrix analysis begins in the next module.